Now that we've learned about EC2 instances and the crucial role they play in AWS, let's talk about the different types of EC2 instances that are available. Thinking back to our coffee shop analogy, you'll remember that EC2 instances are like our employees in that they serve client requests. If we want to have a cafe that can serve a lot of customers, then we're probably going to need multiple employees, right? And they all can't just be cashiers. We also need someone to make the drinks, someone to handle the food, and maybe someone to do that cool latte art that our customers love so much. Like any business, there are a variety of tasks that need to be done, and they often require different skill sets. If we want our business to operate as efficiently as possible, it's important to make sure that an employee's skill set suits their role. In the same way that our coffee shop has different kinds of employees, AWS has different types of EC2 instances that you can spin up and deploy into your AWS environment. Each instance type is grouped under an instance family and are optimized for certain types of tasks. Instance types offer varying combinations of CPU, memory, storage, and networking capacity and give you the flexibility to choose the appropriate mix of resources for your applications. The different instance families in EC2 are general purpose, compute optimized, memory optimized, accelerated computing, and storage optimized.
Okay, so I'm making some notes here. We have different types of EC2 or instances. So EC2 basically means Amazon Elastic Compute Cloud. Okay, it is a virtual server. So the virtual server is grouped under different family, under a family group. So there are different types of instances, EC2. So we have general purpose, compute optimized, memory optimized, accelerated computing, storage optimized. So basically, for each instance, there are different types of servers, right? If you want a general purpose optimized, so there is general purpose, compute optimized, memory optimized, okay? accelerated computing, storage optimized. So you can choose which one is fit for your needs based on this feed, based on the types of instances. So let me explain further.
General purpose instances provide a good balance of compute, memory, and networking resources, and can be used for a variety of diverse workloads like web servers or code repositories. Compute optimized instances are ideal for compute intensive tasks like gaming servers, high performances, and general purpose instances provide a good balance of compute, memory, and networking resources, and can be used for a variety of diverse workloads like web servers or code repositories.
Okay, so the general purpose could be for something not very intensive, right? So we are talking about some applications are compute intensive. They take a lot of computing, a lot of resources. So if you have for the web servers, so the example of general purpose is web servers, right? And web servers and a code repository. So a code repository meaning for people who do not know, if you have a website, you should have a source code. So the source code is called, you can save it somewhere, right? Either on GitHub. I would not recommend Amazon AWS if you have a, but if you just want to do a repository for your code, if you want to save it somewhere, I would recommend GitHub if you have only one, right? One or two codes. The reason, if you have a different, I don't know, servers, many servers or many activities that require intensive computing, then you can move everything to AWS. Okay, so code repository. Okay, what's the next one?
Compute optimized instances are ideal for compute intensive tasks like gaming servers, high performance computing or HPC, and even scientific modeling. Similarly, memory optimized instances are good for memory intensive tasks, as instances are good for memory optimized. Similarly, memory optimized instances are servers, high performance computing or HPC, and even scientific modeling.
So compute optimized, in this case, it takes a lot of work for the gaming, right? If you have a gaming servers, you need a system that's highly performing. I'm going to give you an example of laptop. There are some laptops designed specifically for games, because games, they require a lot of CPU, a lot of computing, and they use a lot of power. So you need to have the hardware that will be able to support. That's the I'm giving you the example of laptop because I've dealt with laptop in the past. And there are specific laptops for games because they are fit for that. It takes a lot of compute. So let's suppose if you have a simple laptop, HP, that you use for your work, you cannot have, let's say, Fortnite software installed in it because the hardware is not compatible for the requirements of the software, because it requires a lot of power, a lot of computing. So it's the same here in terms of the server, right? If you're a company that has gaming, and you need to have servers that are fit, are high performing servers for your data. So you cannot have any servers. It has to be specific, compute optimized, as he said. So this is the example that I dealt with before. I'm not quite sure about the scientific modeling. Probably, yeah, maybe design, right? They do design models. I'm not familiar, but it's probably compute intensive, so that's why it is listed over there. So compute optimized. The example I would take is servers that require a lot of power and a lot of CPU, or a lot of performance. So we can add compute intensive tasks, right? So the gaming servers, this example, right? Okay, high performing computing. It could be any high performance computer. Okay, scientific modeling. There could be other examples. That's just a few examples. All right, let's go to here.
Similarly, memory optimized instances are good for memory intensive tasks. Accelerated computing are good for floating point number calculations, graphics processing, or data pattern matching, as they use hardware accelerators. And finally, storage optimized are good for, can you guess it? Workloads that require and graphics processing or data tasks. Accelerated computing are good. Memory optimized instances are good for
Memory optimized, right? So for the memory optimized, what I can think of is if your servers save a lot of files, right? A lot of files. Let's suppose a lot of documents. Okay. Let's take the example of TurboTax. Right? They do a lot of tax returns and tax paperwork. So if you submit those files, they have to save it somewhere, and they have to save it in the cloud. So in that case, the company have to make sure that they have a lot of memory for their data. So I think that's what he means by memory optimized. And accelerated computing,
for memory intensive tasks. Accelerated computing are good for floating point number calculations, graphics processing, or data pattern matching, as they use hardware accelerators.
accelerated computing, floating point numbers, graphic processing, data pattern matching, utilize hardware accelerators. Okay. Okay.
Accelerators. And finally, storage optimized are good for, can you guess it? Workloads that require high performance for locally stored data. Now, if we map this back to our coffee shop, our cashier becomes a memory optimized EC2 instance, baristas become compute optimized instances, and our latte art employee is an accelerated computing instance type. And there you have it, EC2 instance types.
EC2 instance type. So for the EC2 instance types, we have general purpose compute optimized, memory optimized, accelerated computing, storage optimized. So this one requires a lot of accelerated computing. It's an example of storage optimized. I think this one requires a lot of data storing. This accelerated computing. This one requires for high performance graphic processing. All right, so let's move on. What do we have? Okay, Amazon EC2 instance types that are optimized for different tasks. When selecting an instance type, consider the specific needs of your workloads and applications. This might include requirements for compute, memory, or storage capabilities. General purpose instance. Okay, yeah, we went there. Let's read it. General purpose instances provide the balance of compute, memory, and networking resources. You can use them for a variety of workloads such as application servers, gaming servers. Gaming servers. I thought the gaming servers was for compute optimized. Backend servers for enterprise application, small and medium databases. Suppose that you have an application in which the resource needs for compute, memory, and the networking are roughly equivalent. You might consider running it on a general purpose instances because the application does not require optimization in any single resource. Okay. General purpose. So for the general purpose instances, we do have example of application servers, gaming servers, backend servers for enterprise applications, small and medium databases. Compute optimized. Compute optimized instances are ideal for compute-bound applications that benefit from high performance processors. Like general purpose instances, you can use compute optimized instances for workloads such as web application and gaming servers. However, the difference is compute optimized applications that are ideal for high performance web servers, compute intensive application servers, and a dedicated gaming servers. You can also use compute optimized instances for batch processing workload that require processing many transactions in a single group. Memory optimized instances. For memory optimized instances are designed to deliver fast performance for workloads that process large data sets in memory. In computing, memory is a temporary storage area. It holds all the data and instruction that is central processing unit. CPU needs to be able to complete actions. Before a computer program or application is able to run, it is loaded from storage into memory. This preloading process gives the CPU direct access to the computer processing. So the memory is basically preloading, right? Preloading of the data. Okay. Suppose that you have a workload that requires large amounts of data to be preloaded before running an application. This scenario might be a high-performance database or a workload that involves performing real-time processing of a large amount of unstructured data. In these types of use cases, consider using a memory-optimized instance. Memory-optimized instances enable you to run workloads with high memory needs and they receive great performance. Accelerated computing instances. Okay. Accelerated computing instances use hardware accelerator or coprocessor to perform some functions more efficiently than it's possible in software. Floating point number calculations, graphics processing, and data product matching. Okay, levels. Floating point number calculation, graphics processing, and data pattern matching. In computing, a hardware accelerator is a component that can expedite data processing. Accelerated computing instances are ideal for workloads such as graphics applications, game streaming, and application streaming. Storage optimized instances. Storage optimized instances are designed for workloads that require high sequential rate and the right access to raw datasets and local storage. Examples of workloads suitable for storage optimized instances include distributed file systems, data warehousing, OS application, and high frequency online transaction processing. In computing, the term input-output operation per second is a metric that measures the performance. It indicates how many different input or output operations a device can perform in 1 second. Storage optimized instances are designed to deliver tens of thousands of low latency random IOPS to applications. Input output operation per second. You can think of input operations as data put into a system, such as a record entered into a database. An output operation is data generated by a server. An example of output might be the analytics performed on the records in database. If you have an application that has high IOPS requirement, a storage optimized instance can provide better performance over other instance types not optimized for this kind of use. Okay, let's go back to so which Amazon EC2 instance type is suitable for data warehousing applications? Got a memory, so data warehousing. You see, so this is a warehouse that processes data applications. So memory optimized storage, general purpose computing. So that's gonna be storage optimized. That's for data warehousing applications. So the reason I chose this is this application which receives a lot of data, store a lot of data on their server, they need a storage optimized. Okay. And the second one is, the answer is correct, by the way. Which Amazon EC2 instance types balances compute, memory, and networking resources? Okay. So which Amazon C2 instance type balances compute, memory, networking resources? So that memory optimized, storage optimized, general purpose, compute optimized. So that's going to be general purpose. General purpose. Okay. All right. Which Amazon EC2 instance type is ideal for high performance database? High performance database. compute optimize. I'm sorry. This is tricky. High performance databases. Okay, so for databases, meaning it will store data, right? A lot of data. So if you do in a client server model, if you do a request to the server to retrieve a file, and, you need, because that's going to be on a different scale. A lot of people do it. A lot of people do the request. So in that case, you need a database that has memory optimized, right? So that it can preload faster for you to be able to get the output. So that we go with a memory optimized. That's correct. Which Amazon EC2 instance types offers high performance processors? High performance processors. So we are dealing with hardware. So the first one is memory optimized, storage optimized, general purpose, compute optimized. So that's going to be compute optimized. High performance processor. All right, so what do we have? We are done on this one. Let's go to the next. Amazon EC2 pricing.
We talked about EC2 instance types, but you're all probably wondering, how much is this going to cost me? Well, don't fret. For EC2, we have multiple billing options available. The first one, and the one that most people are familiar with, is called on demand. What that means is that you only pay for the duration that your instance runs for. This can be per hour or per second, depending on the instance type and operating system you choose to run. Plus, no long-term commitments or upfront payments are needed. This type of pricing is usually for when you get started and want to spin up servers to test out workloads and play around. You don't need any prior contracts or communication with AWS to use on-demand pricing. You can also use them to get a baseline for your average usage, which leads us to our next pricing option, Savings Plan. Savings Plan offers low prices on EC2 usage in exchange for a commitment to a consistent amount of usage, measured in dollars per hour for a 1 or 3-year term. This flexible pricing model can therefore provide savings of up to 72% on your AWS compute usage. This can lower prices on your EC2 usage regardless of instance family, size, OS, tenancy, or AWS region. This also applies to AWS Fargate and AWS Lambda usage, which are serverless compute options that we will cover later in this course. Another option is reserved instances. These are suited for steady-state workloads or ones with predictable usage and offer you up to a 75% discount versus on-demand pricing. You qualify for a discount once you commit to a 1 or 3-year term and can pay for them with 3 payment options. All upfront, where you pay for them in full when you commit, partial upfront, where you pay for a portion when you commit, and no upfront, where you don't pay anything at the beginning. The next option is spot instances, and they allow you to request spare Amazon EC2 computing capacity for up to 90% off the on-demand price. The catch here is that AWS can reclaim the instance at any time they need it, giving you a 2-minute warning to finish up work and save state. You can always resume later if needed, so when choosing spot instances, make sure your workloads can tolerate being interrupted. A good example of those are batch workloads. And finally, we have dedicated hosts, which are physical hosts dedicated for your use for EC2. These are usually for meeting certain compliance requirements, and nobody else will share tenancy of that host.
Okay, let's go back to the previous instance, the types of instances. I just want to recap. I don't want to forget that. So for the EC2 type of instances, we have a general purpose, right? Memory optimized, okay? Accelerated computing. We have what do you call compute optimized, and we also have accelerated computing, general purpose, memory optimized, compute optimized, accelerated computing, and what else? Yeah, storage. So there are five: storage and optimized. Just want to keep in mind storage. Okay. Oof. Yeah, let's do so,
We talked about EC2 instance types, but you're all probably wondering, how much is this going to cost me? Well, don't fret. For EC2, we have multiple billing options available. The first one, and the one that most people are familiar with, is called on demand. What that means is that you only pay for the duration that your instance runs for. This can be per hour or per second, depending on the instance type and operating system you choose to run. Plus, no long term commitments or upfront payments are needed. This type of pricing is usually for when you get started and want to spin up servers to test out workloads and play around. You don't need any prior contracts or communication with AWS to use on demand pricing. You can also use them to get a baseline for your average usage, which leads us to our next pricing option: Savings Plan. Savings Plan offers low prices on EC2 usage in exchange for a commitment to a consistent amount of usage, measured in dollars per hour for a 1 or 3 year term. This flexible pricing model can therefore provide savings of up to 72% on your AWS compute usage. This can lower prices on your EC2 usage regardless of instance family, size, OS, tenancy, or AWS region. This also applies to AWS Fargate and AWS Lambda usage, which are serverless compute options that we will cover later in this course. Another option is reserved instances. These are suited for steady state workloads or ones with predictable usage and offer you up to a 75% discount versus on demand pricing. You qualify for a discount once you commit to a 1 or 3 year term and can pay for them with three payment options: all upfront, where you pay for them in full when you commit; partial upfront, where you pay for a portion when you commit; and no upfront, where you don't pay anything at the beginning. The next option is spot instances, and they allow you to request spare Amazon EC2 computing capacity for up to 90% off the on demand price. The catch here is that AWS can reclaim the instance at any time they need it, giving you a 2-minute warning to finish up work and save state. You can always resume later if needed, so when choosing spot instances, make sure your workloads can tolerate being interrupted. A good example of those are batch workloads. And finally, we have dedicated hosts, which are physical hosts dedicated for your use for EC2. These are usually for meeting certain compliance requirements, and nobody else will share tenancy of that host.
Okay, let's go. Go with the EC2. Incorrect. Huh? Standard reserve instances.
We talked about EC2 instance types, but you're all probably wondering, how much is this going to cost me? Well, don't fret. For EC2, we have multiple billing options available. The first one, and the one that most people are familiar with, is called on demand. What that means is that you only pay for the duration that your instance runs for. This can be per hour or per second, depending on the instance type and operating system you choose to run. Plus, no long-term commitments or upfront payments are needed. This type of pricing is usually for when you get started and want to spin up servers to test out workloads and play around. You don't need any prior contracts or communication with AWS to use on-demand pricing. You can also use them to get a baseline for your average usage, which leads us to our next pricing option, Savings Plan. Savings Plan offers low prices on EC2 usage in exchange for a commitment to a consistent amount of usage, measured in dollars per hour for a 1 or 3 year term. This flexible pricing model can therefore provide savings of up to 72% on your AWS compute usage. This can lower prices on your EC2 usage regardless of instance family, size, OS, tenancy, or AWS region. This also applies to AWS Fargate and AWS Lambda usage, which are serverless compute options that we will cover later in this course. Another option is reserved instances. These are suited for steady state workloads or ones with predictable usage and offer you up to a 75% discount versus on demand pricing. You qualify for a discount once you commit to a 1 or 3 year term and can pay for them with 3 payment options: all upfront, where you pay for them in full when you commit; partial upfront, where you pay for a portion when you commit; and no upfront, where you don't pay anything at the beginning. The next option is spot instances, and they allow you to request spare Amazon EC2 computing capacity for up to 90% off the on demand price. The catch here is that AWS can reclaim the instance at any time they need it, giving you a 2-minute warning to finish up work and save state. You can always resume later if needed, so when choosing spot instances, make sure your workloads can tolerate being interrupted. A good example of those are batch workloads. And finally, we have dedicated hosts, which are physical hosts dedicated for your use for EC2. These are usually for meeting certain compliance requirements, and nobody else will share tenancy of that host.
So we have a good idea now on the basics of EC2 and how it can help with any compute needs, like making coffee. Well, like metaphorically making coffee. The coffee represents the whatever your instance is producing. The next thing we want to talk about is another major benefit of AWS, scalability and elasticity, or how capacity can grow and shrink based on business needs. Here is the on-prem data center dilemma. If your business is like 99% of all businesses out in the world, your customer workloads vary over time, perhaps over a simple 24-hour period, or you might have seasons where you're busy and weeks that are not in demand. If you're building out a data center, the question is, what is the right amount of hardware to purchase? If you buy for the average amount, the average usage, you won't be wasting money on average. But when the peak loads come in, you won't have the hardware to service the customers, especially during the critical moments that you expect to be making all your results. Now, if you buy for the top max load, you might have happy customers, but for most of the year, you'll have idle resources, which means your average utilization is very low. And I've seen data centers with average utilization under 10% just out of fear of missing peak demand. So how do you solve the problem on premises? Well, the truth is you can't. And here is where AWS changes the conversation entirely. What if you could provision your workload to exactly the demand every hour, every day? Well, now you have happy customers because they can always get the services they want. And you have a happy financial officer because they get the ROI your company needs. And here's how it works. Morgan is behind the counter. She's taking orders. And we have a decoupled system. Morgan isn't doing all of the work here, so we need somebody making the drinks. Looks like Rudy's up. Now, the first problem I want to solve is the idea that we plan for a disaster. There's a great quote by Werner Vogel that says, "Everything fails all the time, so plan for failure and nothing fails." Or in other words, we ask ourselves, what would happen if we lost our order-taking instance? Well, we'd be out of business until we get another person to work the line. Sorry, another instance up and running. So here is where AWS makes it really simple. Using the same programmatic method we used to create the original Morgan, we can create a second Morgan. So if one fails, we have another one already on the front line and taking orders. The customers never lose service. Well, and don't forget about the back end. Let's make our processing instances redundant as well. So that gets our regular operating capacity. We now have a highly available system with no single point of failure. And as long as the number of customers in line stays the same, we're good. But you know that's going to change, right? So let's take a look at what's going to happen when we have a rush of customers, an increase in demand.
Scaling.
Now, there are two ways to handle growing demands. You can scale up or scale out. Scaling up means adding more power to the machines that are running, which might make sense in a few cases, but think about it. When you have an increase in customers, a bigger instance of Morgan really can't take a customer's order any faster because that depends on the customer more than Morgan.
I'll take an espresso. Oh wait, is that organic? Make it a soy latte. Actually, I don't know. Do you just have tea?
What we need are, well, more Morgans. Customers? Oh no, looks like the processing instances are about to get overloaded. So Let's scale them as well.
Obvious question is obvious. How come there are more order taker instances than order makers?
Well, in this case, the amount of work you can get done is still more than the order machines can send your way. You don't have a backlog, so no reason to add more worker instances. This is one of the great things about decoupling the system. You can end up with exactly the right amount of power for each part of your process, rather than over provisioning to solve a separate problem. Okay, looks like we just cleared that rush. Now here's where AWS really makes a difference to your business. All these extra workers that are now sitting around idle, if you don't need them, send them home or stop the instances. Amazon EC2 autoscaling adds instances based on demand and then decommissions instances when they are no longer needed. This means that every minute of the day, you always have the correct number of instances. Happy customers, happy CFO, happy architecture. So we solved the scaling problem with Amazon EC2 autoscaling. But now we've got a bit of a traffic problem, don't we? Let's take a look at the situation. When customers come into the coffee shop, right now they have 3 options for which cashier to talk to place an order. And oddly enough, most of them are lining up in one line, causing an uneven distribution of customers per line, even though we have other cashiers waiting to take orders, standing around doing nothing. Customers come in and aren't sure exactly where to route their order. It would help a lot if we added a host to the situation. A host stands at the door, and when customers come into the coffee shop, they tell them which line to proceed to for placing their order. The host keeps an eye on the cashiers taking orders and counts the number of people in line each cashier is serving. Then it will direct new customers to the cashier that has the shortest line, is the least bogged down, thus allowing the lines to be even across cashiers and helping customers be served in the most efficient manner possible. The same idea applies to your AWS environment. When you have multiple EC2 instances, all running the same program to serve the same purpose, and a request comes in, how does that request know which EC2 instance to go to? How can you ensure there's an even distribution of workload across EC2 instances? So not just one is backed up while the others are idle, sitting by. You need a way to route requests to instances to process that request. What you need to solve this is called load balancing. A load balancer is an application that takes in requests and routes them to the instances to be processed. Now, there are many off-the-shelf load balancers that work great on AWS. And if you have a favorite flavor that already does exactly what you want, then feel free to keep using it. In which case, it will be up to your operations team to install, manage, update, scale, handle failover and availability. It's doable. Odds are what you really need is just to properly distribute traffic in a high performance, cost efficient, highly available, automatically scalable system that you can just set and forget. Introducing Elastic Load Balancing. Elastic Load Balancing, or ELB, is one of the first major managed services we're going to talk about in this course. And it's engineered to address the undifferentiated heavy lifting of load balancing. To illustrate this point, I need to zoom out a bit here. To begin with, elastic load balancing is a regional construct. Now, we'll explain more of what that means in later videos, but the key value for you is that because it runs at the region level rather than on individual EC2 instances, the service is automatically highly available with no additional effort on your part. ELB is automatically scalable. As your traffic grows, ELB is designed to handle the additional throughput with no change to the hourly cost. When your EC2 fleet auto-scales out, as each instance comes online, the auto-scaling service just lets the elastic load balancing service know that it's ready to handle the traffic, and off it goes. Once the fleet scales in, ELB first stops all new traffic and waits for the existing requests to complete, to drain out. Once they do that, then the auto-scaling engine can terminate the instances without disruption to existing customers. ELB is not only used for external traffic. Let's look at the ordering tier and how it communicates with the production tier. Right now, each front-end instance is aware of each back-end instance. And if a new back-end instance comes online in this current architecture, it would have to tell every front-end instance that it can now accept traffic. This is complicated enough with just half a dozen instances. Now imagine you have potentially hundreds of instances on both tiers, each tier shifting constantly based on demand. Just keeping them networked efficiently is impossible. Well, we solve the back-end traffic chaos with an ELB as well. Because ELB is regional, it's a single URL that each front-end instance uses. Then the ELB directs traffic to the back-end that has the least outstanding requests. Now, if the back-end scales, once the new instance is ready, it just tells the ELB that it can take traffic and it gets to work. The front end doesn't know and doesn't care how many back-end instances are running. This is true decoupled architecture. There's even more that the ELB can do that we'll learn about later, but this is good enough for now. The key is choosing the right tool for the right job, which is one of the reasons AWS offers so many different services. For example, back-end communication. There are many ways to handle it, and ELB is just one method. Next, we'll talk about some other services that might work even better for some architectures.